Okay, so yeah, the burning question on your minds, it's come up in a couple of questions is, I've told you in all these instructions, like what state, the qubits get to you if you apply this instruction on a basic state. And, if they're classical reversible instructions, we know they get you to some other basic state. So we know exactly what happens if you just like keep doing a bunch of classical reversible instructions. But, there's superposition creating instructions like this Hadamard, and you do this like, on a new qubit, and now you're in the state root half amplitude on 0, root half amplitude on 1. And like now you do some instruction, then what happens? Well, that's what we got to talk about now. So instead of me immediately telling you what happens, I want to take a short digression. I want to take a digression to tell you about something I call probability trees. And how you can use them to analyze probabilistic computation. So I'm going to like install your intelligence a little bit by forget everything about quantum for like 10 minutes. We're going to talk about like a non-quantum topic. Just forget everything. We're going to talk about a non-quantum topic for 10 minutes. We're going to talk about probabilistic computation, not quantum computation, but probabilistic computation. And there's a couple of reasons why I'm going to take this digression into probabilistic computation. It's really an excellent analog for quantum computation. And in fact, the laws of probabilistic computation are, I think, like pretty intuitive and familiar, especially if you've taken like 259 or analogous plus like you have. I think like, when I show some probabilistic code and then like analyze all the probabilities, you'd be like, yeah, I get it. It makes sense. But I want to do it because the laws and rules for how to analyze quantum code are literally exactly the same. They're literally exactly the same, except every time you're about to say the word probability, just say the word amplitude instead. And then it's literally the same. Moreover, as you know, quantum computation, to study it, you need to know at least a little stuff about probability, because we have this law of quantum measurement that explains if you get some qubits into a certain superposition state and you do extract all, like what are the probabilities, you'll see different possibilities on your screen. So probability is like an inherent aspect of quantum computation. Therefore, it doesn't hurt to remember a little bit about probabilistic computation. So what I mean by probabilistic computation is, just imagine you have like regular old deterministic code, but then like you get that one magical instruction that lets you have like randomness in your code, probability in your code. And when that happens, you need to remember a little bit about the rules of probability to analyze like how all the bits in your code change values in a probabilistic fashion. So I'm going to remind you about that. Just to make the analogy with quantum computing more obvious, I'm going to, well, for simplicity, or I don't know, sure, simplicity. It's not even simplicity, but for analogy, I'm going to only study probabilistic code that has these properties. So the variables will all be bits. They're all going to be of data type bit. And my deterministic regular instructions will all be classical reversible instructions. Now, they don't have to be. Of course, in regular code, you can use any kind of bit instruction. But, just to make the analogy clear, I'm going to happen to only give you examples that use the classical reversible instructions, but like on bits. And then I'm only going to use like one kind of like RNG type instruction, only one like instruction that generates probability. And it won't be the one for the homework, just to like, I don't know, mix things up. It won't be the instruction that like gives you a 50-50 random bit. It's going to be this new one that I'll call noise on B. Okay, so B is the name of a bit valued or a bit type random variable. And what does noise B do? It toggles B with probability 1/3. Why 1/3? I just made it up. This is just like I made up this instruction called noise just for pedagogical purposes. Toggles it with probably 1/3. Or you can think of it as like, oh, if randint 3 equals 1, then toggle B, else don't toggle B. And you might notice that you could make a matrix or a path diagram for this noise instruction too. It would just be that like the labels now would be probabilities, not amplitudes. So like the path diagram for this noise instruction would look like this: 0, 1. I don't put the angle brackets around it because they're not qubits. These 0 and 1 are just bits. 0, 1. And if you look at it, 0 goes to 0 with probability 2/3. 1 goes to 1 with probability 2/3. 0 goes to 1 with probability 1/3. And 1 goes to 0 with probability 1/3. Okay, so now again, the labels on the edges are probabilities, not amplitudes. But it's kind of the same. Like if you start at 0, you do noise, you kind of get to the state 2/3 probability on 0, 1/3 probability on 1. So very similar to like what we were talking about before, just we're always saying the word probability instead of amplitude. Okay, so now I'm going to write some probabilistic code down. This probabilistic code, it's not trying to do anything. It has no purpose. It's just like I picked some instructions out of a hat and put them in a row. So we're not trying to care what this code does. It's just for illustrative purposes. Okay, but probabilistic code example. Okay, it's like a little function. It's going to have 7 instructions. And they're kind of random. It's just new bit. Oops, new bit A and B. I'll call my variables here lowercase a and lowercase b. Toggle A. I'm going to assume again that like when bits are newly initialized, they get the value 0. Now I'm going to do noise on A. Now I'm going to do if A, then toggle B. I'm going to do noise on B. Then I'm going to do if B, then toggle A. Again, there's no real point here. I just made this up. Then noise on B. And you know what all the instructions mean, and what noise means is said right there. So now if this was like, I don't know, 259 or some other basic probability class, I might say something like, okay, if we did print all now, you know, with what probability do you see all the possibilities? What's the probability of seeing 0, 0, 0, 1, 1, 0, and 1, 1? This is like A and B's values. If I asked you this, you could be like, okay, I could do it. Like, give me a sheet of paper and I'll like work it out. It's like a little bit annoying. But let me show you like a systematic way which you could do it, and you'll agree that like, yes, this works. And then we'll use exactly that same systematic way to analyze quantum code. Okay. And what this way of sort of systematically analyzing probabilistic code, I call probability trees. When I teach 259, I do exactly this in 259. I'm like, this is on lecture 1. This is how we analyze probabilistic experiments. And if there was no randomness in the code, then you would do the thing that's called like tracing in computer science. You just go through the thing step by step and like remember like all the variables values and how they change as you go through step by step. Now, when there's like randomness in the code, like, there's branching, you like branch into different worlds depending on like how the randomness turned out. And you just got to keep track of literally all those branches of possibilities. So it's kind of annoying, but we do it. So in the probability tree, we're going to always be keeping track of the values of the variables. And there's 2 variables here, A and B, and we're going to write them like this. So they start out 0, 0. So like, in some sense, like this line, gets us to here. Okay, and then we do like the next instruction, we just like trace through. So like we're toggle A and we're like, oh, great, this is a simple instruction. When we toggle A, we just get to like 1, 0. But I'm not going to leave it at that. I'm going to draw a line here, very much like in the path diagrams. I'm going to draw a line or an arrow, and I'm going to label this arrow with 1. And that's to signify like, with probability 1, we get to this state. It's kind of obvious because it's like a deterministic instruction. There's no randomness, but I'll just like spell it out. Like with probability 1, we go from here to here. That's what is signified so far. Now we come to like an instruction that has like some randomness in it. So like, we have to branch into like two different worlds depending on like what happens. So we're going to do noise on A. B is ignored, so B is going to stay 0, but A is 1. So 2/3 of the time it'll stay 1, and 1/3 of the time it'll get toggled to 0. I always like to put my zeros on the left and my ones on the right. So I'm going to do it like this. We have like a branch here. We can branch into the world where A got toggled. That happens with probability 1/3. And we can branch into the world where A didn't get toggled. That happens with probability 2/3. Okay. Hopefully this makes sense. Okay, then the next line says like if A, then toggle B. And we're like, well, I just have to like now keep track of two, I'm making a tree here. I have to keep track of like two completely, different world trees. I have to recurse the same process on each of these situations. So I'm like, okay, in this world, like A is 0, B is 0, so A is not true, so we don't toggle B, so we just stay 0, 0. And we like say like, okay, that happens with probability 1. In this world, A is 1 and B is 0, so we do toggle B and we get to like 1, 1. And that happens deterministically with probability 1. Okay. Now we come to the next line, line 5, and we're like, oh man, this is annoying. Noise B. So we're gonna have more branching here. So we're like, okay, it's gonna be branching like here, 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 here. Here, A is 0, it doesn't change. B might change to either 0 or 1. We're noising B, so the chance that it stays 0 is 2/3. Chance that it gets toggled to 1 is 1/3. Okay, over here, what are we doing? Noise B, so 1, 0, that's 1/3. 1, 1, that's 2/3. Okay, now we're doing if B, then toggle A. So that's a little bit annoying, but okay, it's 0, 0 with probability 1. This is actually 1, 1 with probability 1. This is 1, 0 with probability 1. This is B, then toggle A, 0, 1 with probability 1. I'm going to do it. I'm going to noise B. It's like very annoying because we have to like branch, but okay. Actually, the fact that it's very annoying it's intriguing. It actually indicates that if you want to actually compute all this, you need like to do an exponential amount of work, exponential in the number of branching operations, really. So it's kind of funny that you can just run this code and it's like no problem, but like the analysis of this code under the hood takes like an exponential amount of work. Anyway, I'm going to copy off my paper here just so I don't mistake. Okay, 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1. If you detect an error, let me know. I assume you'll be like a little bit too lazy to try to detect an error, but we'll do it. Okay, so that's the last instruction. Now I'm gonna like write something down here. So these are sort of like all the possibilities, like all the worlds that could have happened. But I want to write at the bottom what I'll call the probability outcomes, which is the probability of each of the possible traces. So each of these like paths down to a leaf are outcome probabilities. Each of the paths down to a leaf is like one particular trace that the code could have taken. And I hope you'll agree, like the probability of it taking this trace, let's say this leftmost trace that ends up with A and B being 0, 0, is the product of the probabilities along the paths. That's sort of how probability works, right? So this is 8/27. Why is it 8/27? Because it's like 1 times 1/3 times 1 times 2/3 times 1 times, that's a 2, 2/3. That's 8/27. And the probability that your code like followed this almost same trace, but ended up here with A equals 0 and B equals 1 is like 1 times 1/3 times 1 times 2/3. That's 4/9 so far. Times 1 times 1/3. So that's 4/27. Okay, and the rule is always that the outcome probabilities are gotten by multiplying the probabilities down the path. Uh-oh, there's obviously a mistake. Yeah? Did I multiply it right? Okay, 4/27. Hopefully I did it right. Okay. I will now copy again from my paper. I got like 1/27, 2/27, 4/27, 2/27, 4/27, 8/27. Actually, there's like a nice check I should be able to do here to make sure I didn't make any errors. Like, what check could I run on these numbers?
Just make sure they add.
Yeah, they ought to add 1. 4 plus 2 plus 1 plus 2 plus 4 plus 2 plus 4 plus 8 is 27. So yeah, checked out. Good. So hopefully you're like, yes, this makes sense. Now, to answer this question, like, what's the chance that you'll print out 0, 0? You're kind of not done with the analysis because, like, actually, you see here, there's like a 4/27 chance that the code would do this and end up with 0, 0. But there's actually several ways, well, more than one way you can get to 0, 0. You could also get the final answer of 0, 0 by following this branch that gets you to 4/27. And therefore, the total probability of getting to of 0, 0 is 4/27 plus 4/27, which is 8/27. That's why I had 8/27 in my mind. The total probability of getting to 0, 1, that's 2/27, and 8/27, that's 10/27. To getting to 1, 0 is 1/27 and 4/27, that's 5/27. If we're getting to 1, 1 is 2/27 plus 2/27. That's like 4/27. Again, it's like 18/27, 23/27, 27/27. It adds up to 1. That checks out. Okay, so indeed, like if I said like, okay, if you run this code and then do print all, what's the chance you get like 0, 0? You would say it's 8/27, which is like 29.5%. Okay, and somehow, I remember all this by like once you draw the tree, these are somehow like the sum. All these numbers are like the sum of path products. Like a little slogan. I remember to remember this. Like we get all these things by taking the products of the probabilities along the paths, and then you sum at the end to kind of collate together all the ones that lead to the same outcome. Okay. Make sense? Okay, so hopefully you were like, yeah, I get it. That's fine. And the reason I bring it up is because like you do literally the same thing for quantum code. So I will basically give you the example quickly, but next class will like, take more care. So in quantum code, we just write here for quantum code, we just do the exact same thing, except everywhere we say amplitude instead of probability. So we're going to do the exact same thing, except we'll build what I'll call like an amplitude tree. Okay. So I'm going to actually use the exact same code. Except for a couple small differences. First, following conventions, I'm going to call the variables A and B, or capital A and B, because I don't know, somehow the convention is that we use capital letters for qubits. And these are qubits, not bits, so I'll write new qubit. Toggle is a valid instruction. This is not a valid instruction on qubits. Noise, that doesn't make sense. But we're going to change it to Hadamard. That's the one nice superposition creating qubit instruction. So everywhere, change this to Hadamard. And let me just say, the old probabilistic code I had here is doing something different from the quantum code I did here. Like I made the same example just so I could conserve like board writing space. Like it's kind of a coincidence. Like I just want to say, forget a little bit about the probabilistic code. we're going to imagine you wrote down this like combination of classical reversible instructions and superposition creating instructions. And then I asked the same thing, like if you do extract all now, what's the probability that you'll print out 0, 0, 0, 1, 1, 1, 1, 0, and 1, 1? Now, how do we answer this question? Well, the main thing we have to do is work out this question, like what is the superposition state of, A and B at the end here? Once we know that, it'll be something like, A amplitude on 0, 0. Let me not say A amplitude, like W amplitude on 0, 0, X amplitude on 0, 1, Y amplitude on 1, 0, and Z amplitude on 1, 1. Once we figure out what W, X, Y, and Z are, then we can answer this using the law of quantum measurement, right? Then the probability of seeing 0, 0 will be like W squared and X squared and Y squared and Z squared. So like the main work is to figure out, like after we do all these instructions, like what is the final state? In the same way that here, like we're sort of asked ourselves, once we do all these instructions, like what are the final probabilities on 0, 0, 0, 1, 1, 0, and 1, 1? And I'll do this again next time, but don't rustle up quite yet. But we're going to draw like an amplitude tree. And it's going to work exactly the same. We're going to sort of always be keeping track of like a basic state value for A and B. It's just that these numbers will be different. So I'll get started just to illustrate the point. So, we make new qubit AB. So, OK, that starts them out at 0, 0. First instruction is like toggle A. So we're like, no problem. I mean, we know what happens there. It's like a basic state in, basic state output kind of operation, a classical reversal operation. We just go to A is 1 and B is 0. We still write 1 here, but like now that's the amplitude. That's like the amplitude with which we go to 1, 0. Now the next instruction is like Hadamard A. Okay, so we just illustrate this, and then we'll stop and finish it next time. Hadamard A. So right now we're in the world where like A is 1 and B is 0. So B is not involved in this instruction. So just B stays 0. That's why, like in both of these worlds, like B is just still 0. But A is 1. Now you got to remember, what is the definition of Hadamard? The definition of Hadamard, in particular, if you do Hadamard on basic state 1, you get root half amplitude on 0 and negative root half amplitude on 1. So that's what changes here. You get root half amplitude on 0. So it's like the 1 is changing to 0 with this amplitude. And the 1 changes to 1 or stays 1 with amplitude minus root half. And that's it. Like we did this instruction. Okay, so like this is going to be the same. These 2/3 and 1/3 will change to like various plus root halves and minus root halves. We'll check it next time. And then everything else is the same. Like we are going to multiply all the amplitudes along each path to get these like outcome amplitudes. And we're also going to do this sort of like collation step where we're like, well, you could get to 0, 0 via this path or this path. So we'll like add up these two amplitudes, and that'll be like the final amplitude. But just to answer one question, like a cool thing can happen now because, some of these numbers are negative. So some of these numbers at the bottom could be positive and some could be negative. And so when you do this collation step at the end, you could have like, some positive amplitude of getting to 0, 1 over here and some negative amplitude of getting to 0, 1 over here. And maybe those could cancel out, leaving you with like no amplitude of getting to 0, 1. And that's like kind of the amazing thing that can happen in quantum that can't happen in probability. If probabilities are positive, they can only add up. But in quantum, like you can get like interference where things cancel out. Okay, so we'll do this example in detail next time.